real contact area, then we want to determine the hardness and our Young's module, reduced module. Okay, for the multiple layer thin film 多层的这个薄膜，它的这个杨氏模组跟音符。OK. If the single material you measure the hardness or Young's module, I think you can obtain the fixed value. You can obtain the constant value. This fixed value, I think is no problem. Just the substrate material. Okay, just the single material. Okay. But if your material is made of not just one material, your substrate may be deposited many layers of the same film. Okay. In this case, how do you identify? How do you convince people that your measurement to obtain your hardness and your thin film, your hardness and your reduced module are trustable, are acceptable? Because you will find the Young's module and the reduced module no longer to be the constant value because your real contact area is function of your depth. And then other different depths, you'll find your layer. Okay, there's not you have a few layers over the substrate. So in this case, your hardness and your reduced module just mean that your mechanical property are dependent on your depth. So this is in the future when you measure your thin film material property or your mechanical property, you have to identify first the load you apply, and the second you have first your indentation depth you apply. You have to mention these two properties. Otherwise, different material property, different spin thickness or different indentation depth. You change your indentation depth, you'll find that your hardness and your Young's module are also different. Okay, all right. So this is very, very important because I have read a lot of literature. They give the simple material, give the material property only one value. I just we question this result because this result for these two properties, they are dependent on the indentation depth. Okay, other different indentation depths, your work job in the simple layer, they are also different. So in this case, for the composite film, you obtain your Young's module and your reduced module. It should not be to be just a constant value, not a fixed value. They should be just a variation in some range. This is dependent on your indentation depth. Okay, so this is you have to have this idea. Okay, so how to obtain your reduced module and your hardness. Here hardness is just A. A is function of HC. HC is a function of your indentation depth. So if you have a coating film, the coating film is not just in this case, the coating film maybe have a few layers. In this case, the indentation depth will change your real contact area. Your load, maybe you can change your maximum load to be a fixed value, but this value is totally dependent on your indentation depth. Okay, so in this case, all right, you obtain the real contact area, you obtain the H. This H value, in general case, for the thin film layer, they are dependent on the indentation depth. They no longer to be a constant value. Okay, so you obtain this one, then you can obtain the H. Now you want to obtain the reduced module. Here, okay, HP, please change it because this plot is obtained from another book. Okay, this HP, please change it to be the HC. Okay, HP is HC. The HT is the total phase thickness you obtain from the instrument. is just our HI. Okay. And then our HA, here HA is changed to be our HS. Okay, right? Right. This is from the one book. This is our definition in journal. Okay. In our theoretical development, we use this parameter. Okay. Rather than this one. So we can have the change. Okay. They have the contrast between these three parameters. Okay. All right. Now, this is from the Berkovich indenter, the HP. HP is just our HC. HC is just P. P is load. H is hardness. Hardness is obtained from here. Then we have the relationship. This relationship is obtained from the textbook, handbook. I have shown you last class. Okay, all right. Now the HA is obtained. HA is just our HS. Okay, obtained by this way. Okay, from this equation we can change to be this way. The total HT. HT, what is HT? HT is HI. HI is just the summation of these two terms. This is HP plus the HS. Okay, HC plus HS equal to HI. So these two terms plus together give this one. This is total indentation depth with just HI, right? Okay, this equation can be related to this one. Okay? This P and the HP, this rewritten this equation to be this one. And then this phi and then phi, these two parameters are related to the tangent theta and then sum of the pi and the beta and so on. Okay? So phi and the phi, this change it to be this, change it to be the phi. Okay. Here. Please change it to be no. Change it to be this one. Okay. So this one is just our phi here, right? So this equation related to be this form. So there is these two parameters. They are just related to the tangent theta and then some of the parameter here, some of the value here, like pi and 2 and so on. Okay. So these two values, they are 1.194 and 0.95. Okay. So they are constant. But this equation, given the reduced module, we wanted to obtain this solution. Okay. So in this case, we also have the ER. So this equation also can be rewritten to be the ordinary differential equation of ER. This ordinary differential equation for the ER is the third order, the 三阶的. Okay. So this equation can be have the algebraic manipulation. Okay. 就是用代数的这个操作，给它平均给它平方这些。Finally, from this equation can be changed to be this equation. This equation just used to solve the ER. This is ordinary differential equation for the polynomial equation, not the differential equation. Polynomial equation for ER, all right? Is the third order. Okay, so you use the software very easy to solve the ER. Okay. If those parameters are available, okay, like H is a variable, right? P is not, but the HI is a variable. Okay, phi and the phi, they are the constant value. Okay, so that is from this equation we can obtain the ER. So we can obtain the H. We also can obtain the ER. Okay, for the composite film, it means that you have the substrate coating with a few layers over the surface. Okay. So we show the result. Okay. This show you the plot of the hardness and the reduced module. The hardness is shown here. Okay, all right. You have to take care of this unit. All right. If you obtain some of the units not good, not correct, you mean your result maybe have a problem. Okay, so you have to take care of your result. Some of the material you should have show your measurement, how the value should be match your regular case. We cannot show your material how the value is not consistent with the general case. Okay, so that's very important. Hardness in general, they are vary in the GPA. Gigapart, 10 的90帕。Okay, so for the hard thin film in general, the hardness is just with the GPA. If you have your unit is MPa, megapart, in this case, it's wrong. Okay, that's very important. Okay, because you are engineer student. Okay, you get something, the data is trustable or not. That's very important. Okay, especially in your research and then in the outside when you work in the company. You get something, the data is you can believe it or not. Somebody can convince it or not. That's very important. G in general is GPA if it is hard material. Okay, all right. So this solid curve is predicted by the spherical model. All right, spherical model, and then triangle data are experiment data. Okay, you'll find that your spherical model has good regression over the whole region for your experiment data. Very good regression, very good fitting. So our spherical model, no problem. We find that the curve out here, they have a turning point. The here we also have the turning point. Okay, so in this case, from here, the first turning point, we have the phase change, or we call the transition point. First phase change, we'll talk about later. Okay, we use the Gibbs function to express why here they have a transition. They have a phase transition. Okay, another turning point here is from the second section to the third section. Here we have a pop in. All right. Okay. So the triangle is just the composite field. Evaluate other different indentation depths. First, the square data here. Square data means data. Square data is means data. They are just the substrate material without any coating film. 就是这个方块是底材的材料，没有任何薄膜。Here we have showed the substrate material without any coating film. Okay, the triangle is just the substrate coating with the thin film layer. You will find this that here the data no longer to be the constant value. Your indentation depth will show your data from high indentation depth to the low, relatively low hardness. Okay. Your hardness no longer to be the constant value. Okay, all right? So this is very important. In the future, when you have a coating field, they use the nano indentation to show your property. You have to show me what is the maximum load you obtain. Maximum load you set, you have to show it. The second, what is the indentation depth you give it. Maximum indentation depth, you have to show me, okay, and then your loading rate, I will have to show. Okay. So that is all these parameters for your indentation depth. They are important. So you have to show it clearly, not just the final value, okay, because they are no longer to be a constant value. They are very with your indentation depth. That's very important. Because in the future, when you have an electric or optical product, you have to sell to the buyer. Okay, you have to sell to a buyer. The buyer will ask you to show all the detail of the hardness, whether the material are satisfied the requirement of our order. Okay, that's very important. No doubt. Okay, so there is you have to show the standard way to obtain the detail of your material property. Okay, in your research and then your future work. Okay. And then here you find this triangle data is very close to the square data. It's the mean data if your indentation depth is very large, is sufficient large. You will find that your experiment data of your composite film is much influenced by your substrate. 你的压伸很大的时候，你的薄膜的量到的这个资料会深深的受到你的底材的影响 ，because they are just if indentation depth increase continuously, you'll find that these two curves, these two data, these two set of data, they are close each other. They are close each other. Means that if your indentation depth is too large, you obtain your composite film data is wrong. Is wrong because at that moment your data is much affected by your substrate behavior. 所以你在量很薄膜的时候，你不能量得太深啊，不能量太深。量得太深的时候，你量到的这个薄膜的量是会受到底材的影响，所以量到大部分都是底材的效果。Okay, so if the thin film is very last I have told you that your largest, your highest indentation depth in general is less than 20% of the total thickness. This criteria you have to follow. You have to follow. Okay. If your indentation you don't have make any restriction, you'll find that your hardness actually is much affected by your substrate material. Okay. All right. So in the modern time, if the shaping become more and more less, 越来越少. In this case, you'll find that it's very hard for you because 20% of your total film thickness is become very small, very small. If very small, our size effector, last class we showed the size effector. The size effector included your residual stress, your surface roughness, will influence your indentation. So we have two dilemma. 我们有两个困境。If the film thickness is too small, you cannot have your indentation depth too large. If your indentation depth too small, you will have a surface roughness effect on your data. So you have a big problem. You do this one, you have another problem. You do another problem, you have this problem, the dilemma. Okay. So if you want to measure your thin film to be very small thickness, you have a big trouble, a big challenge. Okay. How to convince other people that you measure your thin film property are trustable, are convincible. Okay. You do small thickness, but you have other factors will influence your indentation. If you have an indentation too large, you'll find that your substrate material property influences your data. Okay. So how to do it? Think about it. Think about it. Because you will find the thin film. There's a lot of layers, but each layer very thin, very thin. Like your IC chipper, IC chip become very thin. Okay, your mobile phone for the last generation, it will become thick. The nowadays become thin and thick. Okay, right. So you'll find that the thin film become less and less. So how to measure the thin film property correctly is big challenge. Big challenge. Okay, so there's a thing about how to do it. All right, there's 4 different principles. Okay, we have and then for this 200 nanometer, we cannot. This is for this curve. For the 100 nanometer and the 50 nanometer for the carbon field, we have the transition turning point, and also have a coupling turning point. Okay, but for your thin film is large to the 200 nanometer. In this case, we cannot find any transition point, and then our copy. We don't have the copy in the phase transition. Okay, so there is just a pop in and the phase transition are two property. When your behavior reach the criteria of this two property, then this two property will happen. Okay, if you are your value not reach the critical point or reach the criteria of this two property, then we don't have this two behavior happen. Okay, so that is dependent on the stress and the strain happen inside of the thin film. All right. Okay. So that is a way I talk about. Now we turn to what is the phase transition? What is the property? Okay, we'll talk about it. We'll discuss in more detail. This is a reduced margin. It's the same. Okay. So in this case, you'll find keep in mind that if your indentation is too large, you'll find that this composite film, the material property is very close to your substrate. It means that your measurement is much affected by your substrate. Now, we try to determine the interface property. This interface property is related to our pop-in. Our pop-in actually is just happen in the thin film interface. Okay, interface. They have to relate to the pop-in. So we try to use experimental data. We use the focus ion beam to cut the specimen and obtain the cross section. And observe the microstructure of the cross section. If the cross section have some of the defect, for example, have the nano scale micro crack, or some of the something. Okay. In this case, if we can find this micro crack or nano crack at the interface, I think we think that the interface of micro crack or nano crack is related to our pop-in. Okay, let me talk about it. Okay. Now, we use the experiment method to observe the cross section of our sample. Okay, and observe some of the phenomena at the interface. Okay. Here show the data from this published literature. Okay, so it's not done by my level. Okay, it's done by other people, published in this journal. Okay, here is the load we apply, and this is the indentation depth. We find the maximum load can be changed. Okay, and then the material is DLC, the diamond-like carbon film. All right. And then we have a different maximum load. Okay. For example, here we have here. Okay, here is pop in because here is happening in the loading process. And then here we'll have the pop out. We'll have a pop out. Okay. But if you change your maximum load, you cannot find the pop in or pop load in some of the maximum load. Okay. But if load is high enough in the maximum load, then we find some of the pop in or pop out in the loading or in the unloading process. Okay, so they have the phase change. They have some of the pop in or pop out. Okay, here they have a slip back. I think this is prepared by the people with the background in the material science. So they use the microstructure to observe the pop in and pop out. They find some slip back here. Okay, they find some of the dislocation. Okay, all right. So this image actually is prepared by the background of the material science. Okay. Now we also have done the same experiment data, but use a different material. We use the data just like us we showed previously. Let me talk about the pop in. Why is the pop in? Okay. And the pop in behavior, more detail we're showing here. Pop in actually is just like this. Here we find that they have a line. This line is just come from the microcrack. What does it mean by microcrack? This is amorphous silicon film. This is carbon film. They have the diffraction, right? Because you have a higher load. You'll find that this amorphous silicon film, its structure is different from your single crystal silicon. So at the interface of the amorphous and the single crystal silicon film, the interface, you'll find they have a crack. They have a crack. Micro crack or nanoscale crack. So this form originally is connected with this single crystal substrate, but now it is separate. So in this case, after load is removed, you'll find that there exists the nanoscale crack over the interface, like this one. Okay. So last one, they showed is a dislocation or something. But if in the engineer scale we observe it by TEM or by the SEM, we find actually is just the micro or nanoscale micro crack. So this micro crack allow this silicon, amorphous silicon, this one is separate from your substrate. They are separate each other. Okay, all right? So let me talk about back. We want to use the spherical model to study our problem. To use the spherical model to describe the pop-in behavior. Okay, here there's a composite film. Composite film in our case is the carbon film and amorphous silicon. Okay, here is the single crystal silicon. They have separate each other with the crevice. Crevice 就是裂隙。All right. The crevice is created between the composite film and the substrate, meaning out of the interface. They have the length is 2A. This A is unknown. Now we use it. Then we want to determine the A. All right. Okay. We have cut the surface. We can observe that they have the length, crevice length is 2A. Very small, very small. Okay. Now we apply the load, and they allow this composite film and the substrate. When load is applied during the loading process, because this material property and this material property, they are different. So there is a diffraction value. Diffraction 就是往下的变形。The diffraction value for the composite film and the substrate, because their material is different. So their diffraction value, 它们变形的量 is different. If different, then they have a crevice during the load is applied. they have the cracks. You can observe it, but actually we cannot observe it. Okay, okay. Because we apply law, we cannot observe the behavior. But you can think about it, they have a purpose during the load applied. Okay. And then we use the membrane theory. 薄膜理论. Membrane theory have showing in our textbook, in the mechanical engineer textbook. There's a lot of membrane theory. We can use the membrane theory for this one. Okay. We have a simple support beam with the rectangular form. This is the top view. This is the rear view. This rear view just this is the same thing. And then they have two support here. Connected the support. This is just 2A. Right? Now we have the load applied here. And then they have a deflection. Just like this. So you can think of this P applied to the simple support fin, because this composite fin have a delaminate from your substrate. Delaminate just torsion. In the thin film preparation, we prepare thin film. We just very worry about that our thin film not have a strong adhesive stress with the structure. So the thin film, whether it's the quality of the thin film, whether it's a good quality or low quality, is totally dependent on this thin film. Whether it's needed large load or small load to separate your thin film and your structure. 你要让一个这个薄膜要让它评估它的一个所谓的附着性，就是你要看它脱层所需要的力量。The force needed to delaminate the thin film from your structure. If the load is large, then in this case it means that your adhesive behavior is good. If the adhesive strength is low, it means that this adhesion is not good. In this case, we need less load to allow this substrate delaminate from your thin film. Okay. So this is delamination is just one way to evaluate the adhesive strength of your thin film over your substrate. Okay. So this is we have it if we have the substrate delaminate from your composite film. Then our membrane seal in general not use the focus load. This is the load, capital load, but big load is mean the load. Okay, capital P mean the capital load, 大写的 P is load. But in general, we use the membrane seal. This membrane seal is developed not by the Fox law. They developed by the pressure distribution over the contact area. Okay. Membrane seal in general was developed by the pressure. So small p is contact pressure. bigger P or capital P is the load you apply. Okay, keep in mind. Okay. And in midterm, I'll ask you, all right? In general, the membrane shear is developed by the pressure, contact pressure, rather than the force load. Okay. So in this case, we have to establish the relationship between the P and the capital P. Okay. Load P is given. You apply the external load, that's the value you given. But the uniform pressure over this surface created the same behavior, the same crevice. It means that this small p have a relationship with your capital P. We have to develop it. But based on the membrane shear, like this is a simple support beam. Okay, with the top surface is just a rectangular surface, right? And then we have the two support here. So these simple support beams connect with the two sides, other two sides, fixed. There is no deformation, right? And then we have the P. This P up to now, it is still a known value, but we're assuming it is a small p. This small p is a uniform distributing over your contact area. Although this cantilever will have a deflection at the midline. This midline originally is horizontal, now it is given the deformation. This deformation, other two sides, we don't have any deformation because they are fixed. They are simple support. But at the midterm, at the mid-length, 就在中央 at the center line, this line, we have the maximum deflection. This maximum deflection we call the W maximum. Okay, at the midpoint. Okay, midpoint, right? And then the curve length or the length of the simple support beam, just do it, just do it, just do it. Okay? So in this case, by the membrane shear, the maximum deflection under the center line, you can find it is this equation. This equation is proportional to our P. It's just the pressure, contact pressure. A, phase A is just 1/2 of the crevice length. Okay? EF, what is EF? Young's module of your thin fin, your composite fin of the Young's module. It's just obtained by your reduced module, and then obtain the thin fin Young's module. Obtain the reduced module first, then you use the reduced module to obtain the Young's module of the thin fin. What is I? I is the area moment of inertia of the cross section. Area moment of inertia of this cross section. Your cross section also the rectangular form. This one with the thin fin thickness, total thin fin thickness. We call the T star. So this area moment of inertia we call the I will show you later. So that from the membrane shear, if the uniform pressure acting over the surface, we have the maximum load and maximum deflection at the central line is just this value. And the moment this gives the P, we have the deflection is this value. We can assume this uniform pressure acting over the surfaces equally to the disk. Now, origin is P, small p over the surface, right? We also can, we don't use the P, but we apply the bending moment, M prime, at the two ends of this cantilever, apply the P. Like this one, apply the bending moment. Then this one, we have the deflection downward. Right? So, it is equally apply the bending moment at the two ends of this simple support B without the P. And then we can create the same maximum deflection at the central line with this way. Okay. So this is just two equations I obtained from the membrane theory. All right? Okay. Now we try to establish the simple mechanism. This simple mechanism is not difficult, but they are available from our membrane theory or so on. You can think of all the same things are just membranes. Membranes may be the soft membranes, maybe the hard membranes. Because they are geometry, they are very same thing. We can consider they are all the membranes. Okay, with different mechanical properties. Okay, all right. So then we have these two forms. Okay, now so we have these two equations, right? Now we use these two equations. We continue to obtain the stress and the strain over this same thing. Okay. Now here there's an indenter. We have the composite fin, and then they have a deflection, right? The total fin thickness we call the T star. We call the T star. Okay, this is maybe the 2 or 3 layers of the same fin, but just a composite fin. All right. And then we apply the indentation load in the down wall. So we created the maxima indentation. We created the maxima deflection in the central line. We call the W maxima. This maxima actually just our real contact depth. Our real contact depth. Alpha is just the half angle of the Bokovic indenter. Okay, this is 72.3 degrees. I remember. Okay. So this same thing have a deflection in this area, right? And then we cut it into the two parts. The half part, this half part of the same fin is subject to the compressive stress. We call the sigma I. The sigma I stress at the central line of this cross section is 0, but it's from 0 to the maximum. But this load in the upside of this same fin is compressive stress, 它是压缩的应力。But in the low side, it's just the tensile stress, 它是张力。Okay, all right. So the internal stress, either in the compressive or in the tensile stress, from the membrane thin, is just this value. So it's this value. It's related to the M prime. M prime is just the torque we apply at the end of the simple support beam. Just the last equation I showed to you. Okay. Right? So the membrane thin theory allow us the internal stress to look like this. So take the M prime from the last equation and substitute into this M prime, we obtain this one. Okay. All right? And then from this equation, we obtain this one, right? And then interchange the I and the sigma I. Sigma I put here, I here. All right? So I the area moment of inertia. Area I equal to sigma I, right? P. Oh, this is 6. P star and A squared, right? I. So from this equation, obtain I is here. This I is input into here. Then you obtain the W maximum, just maximum diffraction in the center line from this equation. Then you obtain this equation. Okay. All right. So the maximum diffraction in the middle line, in the center line, we have this value. This value is just our HC. Our real contact dash is expressed by this form. This equation we call A. Keep in mind, this A equation will be used to determine the stress and the strain within the material inside. Why we need to obtain the stress and the strain? If stress and the strain are available, then we can determine we call the strain energy. This strain and energy is how to define. Is the stress and the strain. This is strain, this stress, and our V. V is what is V? V is the volume. This is what we call the strain. If this strain energy in some of the value is beyond the sum of the critical value, you will find that the same thing, our defect. Our defect here is just pop in. So pop in is a material property. This material property allows this strain energy to be a constant value. What does it mean by constant value? Because if the effect occurs beyond some of the critical value of strain energy, it happens. It means that this behavior is material property. Material properties means that it's dependent on the stress or strain. It's dependent on some of the value. If this value beyond the critical value, this behavior will take place. 我们是很希望刚刚的，我们使用什么条件？我们发觉它的这个量可能不变，可能会变，但是我们用应力应变，再给它做体积分，这个值达到一个临界值的时候，这个行为就发生了。这个行为就发生了。我不管你这个 stress 是怎么发生出来的，反正这个乘积在对它的体积分得到的值超过了一个临界值，它就会发生。Our pop in and our transition behavior, they are independent of operating condition, but they are dependent on the strain energy. You mean the strain energy, they have two critical values. One is for phase transition, one is for pop in. If you are strain energy, when you evaluate this strain energy beyond the critical value, maybe your phase change or your popping will happen, will take place. That's why you need to obtain the internal stress and the strain. Very, very important. The strain energy, any material, how the defect, how a crack, how the dislocation or so on, you'll find that just the strain energy beyond the critical value. The critical value is totally dependent on your material, your sample. Okay, your sample different. Of course, your critical value is different. But if you find the same material, if your strain energy reach the critical value, beyond the critical value, you can predict it, and then you can testify, you can 证实 all the behavior will happen. Okay, the defect will happen, either in phase transition, in material structure change, or in the defect like a dislocation or micro crack. Okay, all right. So same thing, microcrack is a very big challenge for us because there is some strain beyond in some way beyond the critical value. Those defects will happen. Okay, so with 10 minutes break here. Okay, then we continue how to discuss the copying. Okay, find the cause of the copying. 10 minutes.